Okay, so we'll continue our discussion on functions that we started last class. But first, just a quick reminder that we're having a set theory workshop. Okay, it will be, I think, tomorrow between 7:30 to 8:30 PST.
Mhm.
And okay, so we'll introduce new concepts about a function. So you can already notice that we are starting with certain concept, and then we are putting more restrictions on the definition. So we're just limiting, we're dealing with special cases of every time. So at first we dealt with ordered pairs, then we spoke of a special kind of ordered pairs called the graph, and then a special kind of graph called functions, etc. So the concept here would be restriction of a function. So let f from mapping from A to B be a function. So this is a function here that maps from A to B. So it has a domain of A and a range that's a subclass of B. And let C be a subclass of A. By by the restriction of the function to C, what we mean that fc of x equals f of x for all x belong to C. So what this means that I'm just changing my domain from A. I'm just taking a subclass of A and then using the exact same function. And you can already see that fc would be a subclass of f. So this is just basically the same function, but on a smaller domain. I'm restricting what my domain would be. This will become clearer in the next few things, but first, a little theorem about the restriction function. If you have f mapping from B union C into A is a function, then f equals the restriction of f to B union the restriction of f to C. Okay, so I think you'd have 2 minutes to think about why this could be true, and then we'll go through the proof immediately. But just like for 2 minutes, think why this is the case, given the definition that we gave to B and C, that to the restriction of f to B and to the restriction of f to C. So that's just the definition here. So it's the same function, but on a smaller domain. Okay. So you'll have just some time to think why this could be even true. The proof, and just when we ask that you think about the proof for a moment, it's not necessarily the case that you exactly reach the proof, because in general, when we are dealing with set theory, especially during this period, we are more of building mathematical thinking rather than the actual theorems, but the theorems are literally endless. So unlike arithmetic, you don't really expect to know every theorem, but the whole goal of set theory is to change the way mathematics is perceived in general, or the way you think of mathematics. So it's not necessarily that you reach the proof, but just building a specific way of thinking that's very useful in mathematics, namely the abstract way of thinking of things. Okay, so now proceeding to the proof. So if I have xy belongs to f, so the regular method, I assume that xy belongs to f. What this means by the definition of the function that we expressed the last session. So the last session we spoke what the function means, and so from that definition we said that if xy belongs to f, then for all x belongs to B union C, there exists a y belonging to A such that xy belongs to f. So this is just from the definition of a function, what it means that for every element in this domain, there exists at least one element in this codomain, such that xy belongs to f. So it's just a special kind of a graph. So now this can be expressed by the definition of the union. Instead of saying for all x belong to B union C, I can say for all x belong to B or for all x belong to C. So this is just from the definition of the union. Then, and leaving the second part as it is, there exists a y belong to A such that xy belongs to f. And this is just equivalent to saying for all x belong to B, there exists a y belong to A such that xy belongs to f, or for all x belong to C, there exists a y belong to A such that xy belongs to f. So here we are just playing around with the logical operators more than with and with few basic definitions. So just I changed B union C into or for all x belong to B or x belong to C. This statement is true, which is logically equivalent to saying for all x belong to B, the statement is true, or for all x belong to C, the statement is true. And so this just, if you look at this part, this is exactly the definition of the restriction of f to b. That is, for all x belong to b, there exists y belong to a such that x, y belongs to f. This is just the same as the restriction of f to b. And the second part, for all x belong to c, there exists a y belong to a such that x, y belongs to f. This is just the definition of the restriction of f to c. Because if you compare this to the definition of the function from the beginning, you notice that it's the same, and the only thing that's different is the domain here. So you notice for the first part, you had for all x belongs to b union c, then this statement. Here you have for all x belong to b, and the exact same statement. So it's the same function, but the domain here changes from b union c to b, or from b union c to just c. So this is just the restriction of f to b and the restriction of f to c. So what we've just proven is that if you have xy belong to f, then xy would belong to f restricted to b or f restricted to c, which is just f restricted to b union f restricted to c. And the same thing can be argued backwards. So if I have xy belonging to f restricted to b or f restricted to c, then applying the definition of the function, I get this previous statement, and then so I can proceed in both directions while dealing with this kind of statement. And if you can proceed in both directions, so if you can start assuming that xy belongs to f, and then you prove that it belongs to f restricted to b or f restricted to c, or if you can work in reverse, so you assume that xy belongs to f restricted to b or f restricted to c, and then you were able to prove that xy belongs to f, that's the definition of equality. As long as you can work in both directions, then you can say that these two are equal to each other. As usual, if anything in the proof or in the way of thinking itself was not clear, you can just type it in the chat. So a longer theorem about also the restrictions, so it's still in the same concept. If we let f1 map from b to a and f2 map from c to a, and assume that b intersection c is phi, so b and c are two disjoint classes. Okay, so if we define f equal f1 union f2, then these three things hold. First, f mapping from b union c to a is a function, and so it's not just any regular graph, because you can have two functions add together and they give you a graph, but not necessarily a function. Here, what I'm saying that this would be necessarily a function. So all the conditions of a function apply to from f b union c to a. The second statement that f1 equals f restricted to b and f2 equals f restricted to c. And the last statement is that x belongs to b implies that fx equals f1 of x, and x belongs to c implies that f of x equals f2 of x. So that's a longer theorem than the last one, because there are three statements here, and there are more assumptions that we started with. So we assumed two functions, f1 and f2, and assumed that b and c, so the two domains, are disjoint. And then we want to know some features of that new f, which is f1 union f2. We want to find and to prove a few of these properties that apply to f. So as usual, you'll have 5 minutes to think about it. Proceed with the proof of each of these. So first, if we have xy belong to f1, so first I have, from the definition of f1, I have that f1 maps from b to a, and it's a function. And so in this case, you have that if xy belongs to f1, then x belongs to b. That's by definition of the function. Now the second statement, why xy belongs to f, that comes from the fact that f equals f1 union f2. So if I have any element that's in f1, then it's definitely in f, right? Because so if I have any element in f1 or in f2, then it's definitely in f, right? So that's from the definition of the union. So the first part of the statement, that xy belongs to f1, implies that x belongs to b. That's just from the definition of f1. And the second statement, that xy belongs to f, is because f equals f1 union f2. So that's from the definition of the union. So that's the first thing. The second thing I would argue in reverse. If I have xy belong to f and x belongs to b, this would imply that xy belongs to f1 or f2. So why is this the case? Because I have that f equals f1 union f2. So if xy belongs to f, then it's either in f1 or in f2. So that's by definition again. Now, the reason why it cannot belong to f2 and y belongs to f1. So this first line is pretty straightforward from the definition of what f is. So f equals f1 or f2 or union f2. Now why xy belongs to f1 and not f2? That's because of the second statement that x belongs to b. So I have that b intersection c is phi. So if x belongs to b, it definitely does not belong to c. But c is the domain of f2. So if something is not in the domain of f2, then certainly xy would not belong to f2 because x is not even in c. So, and that's because b and c are both disjoint. So the statement that x belongs to b implies that x does not belong to c. And if x does not belong to c, then xy cannot belong to f2. That would be impossible because if xy belongs to f2, then x has to belong to c from the definition of f2 as a function. And so if I have xy belongs to f1 or f2, and xy does not belong to f2, this would already imply that xy necessarily belongs to f1. So now I have, if xy belongs to f1, then it belongs to b, and xy belongs to f. Then x belongs to b, and xy belongs to f. And if the opposite is true, if xy belongs to f and x belongs to b, then xy belongs to f1. So this just implied this double implication that xy belongs to f and x belongs to b, imply that xy belongs to f1, and the opposite is true. The same thing can be argued for c and f2. So just if you replace every b here with c and every f1 with f2, you will get the same result, but for f2 instead and c instead of f1 and b. So this second part is just you will repeat the same argument, but for f2 and c instead of f1 and b, and you reach the exact same result. Now what this is telling me is that if I have x belong to b, and I know that xy belongs to f, then I know that xy belongs to f1. But this is exactly the definition of the restriction of the function. So what the restriction of the function is that if I have xy belonging to a specific function, and I specified x to belong to a subclass of the domain of f, then xy would belong to this restriction. So going back to what restriction was, so it's basically the same function, so f mapping from a to b, but the difference is that I'm changing the domain to c, where c is a subclass of a. So the difference would be seen if I just removed that c. So if I say f of x, that would be for all x belong to a. But as when I restrict it to c, then that's for all x belong to c, which is a subclass of a then. And so you can clearly see that in this case, f1 and fb would be the same, because if xy belongs to fb, then it would then follow necessarily that if xy belongs to f, then x belongs to b. So that's from the definition of the restriction of the function. So this already proves that f1 equals fb and f2 equals fc. So that's the second statement we're trying to prove. And in fact, it also proves the third statement, that if x belongs to b, fx equals f1 of x. If you recall from the last session, we said that another way of writing f of x equals something is to say xy belongs to f. So that's from the last session. So if I have f of x equals y, that means that xy belongs to f. And f1 of x equals y, then xy belongs to f1. And so you can say that this means x belongs to b implies that xy, if xy belongs to f, then xy belongs to f1. And that's the exact same statement that we reached in this case. So if I have xy belongs to f and x belongs to b, then xy belongs to f1, which is just the same, logically equivalent to that statement of x belongs to b, imply that f of x equals f1 of x. So basically when you have two statements and you want to prove that they are the same statement, whatever that you change the form of the statement that you have. So in order to prove that these are the same, I just change f of x and say f of x is the same as xy belongs to f, and f1 of x is the same as xy belongs to f1. So these two statements already prove my second part and my third part. However, still we need to prove the first part, and the first part is that this f is even a function. So from the last session when we spoke when is something a function, we said it must satisfy specific conditions. First, that the domain of f is the same as this first part, and that the range is a subclass of the second part. Okay, so that's for it to be a function in the first place, not just um, any random set of ordered pairs or any graph. So they must fulfill specific condition for them to be functions. And so first, when we spoke about graphs, there was one of the theorems. We said that the domain of F1 union F2 is the same as the domain of F1 union the domain of F2. So the domain of F1 is B because we defined F1 to be a function. And the domain of F2 is C since F2 is also a function. And so this would mean that the domain of F1 union F2 is B union C. So this satisfies the first condition. The second condition is the range of F1 union F2. This would be equivalent to the range of F1 union the range of F2. So since I know that F1 is a function, I know that the range of F1 is a subclass of A. And since I know that F2 is also a function, then I know that the range of F2 is a subclass of A. Because that's the codomain of F2 and F1. So the codomain of F1 is A, and the codomain of F2 is A. And since F1 is a function, then the range is a subclass of its codomain. So the range of F1 is a subclass of A, and the range of F2 is also a subclass of A. And if that's the case, then the union of F1, the range of F1, and the range of F2 would be also a subclass of A. So that's just the old idea that if B is a subclass of A and C is a subclass of A, then B union C would also be a subclass of A. So then from these two statements, I can say that the domain of F is B union C. So F is just F1 union F2. So I'm going to remove F1 union F2 and put F in its place. So then domain of F equals B union C, and the range of F is a subclass of A. So that's the first condition for it to be a function. The second condition, if I have f of x equals y1 and f of x equals y2, I must have that y1 equals y2. So that's the second condition for anything to be a function. And if you compare this to the functions in arithmetic, so for example, if you have f of x equals x squared, for example, if I say x equals 2, I cannot get two different values for this function. I cannot say y equals 4 and y equals any other value. So that's the same thing with ordinary arithmetic. In a function, if you substitute for x, you get only one y value. You cannot get two different y values, or else then it will not be a function. So I'm going to say f of x equals y1 and f of x equals y2. So this would imply that x either belongs to B or x belongs to C, right? Because I have that B and C are both disjoint, okay? And I have that the domain of f is B union C. Then if I have that f of x equals y1 and f of x equals y2, this means that x belongs to the domain of f, which is either B or C. So if I have f of x equals y1 and also equals y2, then x belongs to B or x belongs to C. Now, if we assume that x belongs to B, then from the last part, from is it the last? Yeah, from this last statement, I know that f of x equals f1 of x, right? So I can say that if x belongs to B, then f1 of x equals y1 and f1 of x equals y2. But I know that f1 is a function. And since f1 is a function, this would imply that y1 equals y2. And the same can be argued for C. So if I say x belongs to C from the previous part that we have proven, then this implies that f2 of x equals y1 and f2 of x equals y2. But I know that C is also that f2 is a function, which would also imply that y1 equals y2. So now, if you look at these two conditions that we have just proven, the first is that if I have f of x equals y1 and f of x equals y2, this would imply that y1 equals y2. And the previous condition is that the domain of f equals b union c, that the range of f is a subclass of A. These two conditions combined is what a function is. And so from 1 and 2, I can say that f is a function. So that was a long theorem, and there was a lot of details going into it. But in general, when you're dealing with proofs, especially in set theory or in general in abstract algebra, you do not expect to get the whole proof from just the first glance of looking at the question. You just go step by step till you reach your final conclusion. So you do not really have to recall all this proof at the same time. You just have to walk step by step till you reach your final conclusion, and then that's it. You don't have to remember every single step at the same time. You just have to work through the process rather than remembering the process itself. And that's in general for set theory in any theorem we'll be dealing with in the future. So an example for this, I hope the example makes it clear, but if we are dealing with a function, for example, x equals x squared, sorry, f of x equals x squared. So if I'm dealing from the domain of R to R, I can restrict that from R plus to R. So first, I'm dealing with the same function. So in all cases, f of x equals x squared. What I'm changing is what values can be inputted to x. And so in the first case, I can have x equals 2, -2, negative pi, or whatever in the x. In the second case, however, I can only have positive values for x. So you can already see that I'm just changing my domain. So instead of allowing x to be positive or negative, I'm saying x has to be only positive. Now, the reason why this is even useful, if you think of the first function is not injective. If you remember now, when we talk about injectivity, I can have two different x values that give me the same y value. So if I substitute here for x equal 2, f of x would equal to 4, would be equal to 4. If I substitute for x equal -2, I would also get 4. So I can have the same y value to do different x's. However, in the second case, in the instruction, this will never be the case because there are no two positive real numbers whose square is the same. I can have a positive number squared equivalent to a negative number squared, but I can never have two positive numbers whose square is the same unless these two numbers are equal in the first place. And so when I restrict a function, I can get new properties, new useful properties like for the injectivity of the function. And this is especially useful while dealing with things like functional equations and such things. In general, restricting a function can yield specific properties to a specific domain. That's not necessarily the case for a larger domain, okay? So I hope this example made it a little clearer, the whole idea of restriction. So the whole idea of restriction, I'm just changing the domain while keeping everything the same, nothing more. Okay, so the second concept would be composite functions. So again, that's a special kind of functions. We first spoke about composites while dealing with graphs. And so we said the composite of graph G and H. And in this case, it's exactly the same, but the difference is instead of these two being graphs, these two are this time functions. Okay. So F composite G would be the ordered pair XY such that there exists an element Z where XZ belongs to F and ZY belongs to G. Or in a simpler notation, F composite G would be the case when f of x equals z and g of z equals y. Okay, so then f composite G of x would be just y immediately. Okay, so this is just, I think, a simpler form or a shorter form of notation instead of fighting all this statement. And this form would be especially important while dealing with functions rather than with graphs. So it's the same definition as the graph. The only difference is instead of f and g being arbitrary graphs, this time they are a special kind of graphs, which we call a function. A theorem, again, would be if I have f maps from A to B and g maps from B to C, and f and g are functions, then g composite f from A to C is a function also. So G is not just a graph, it has to be necessarily a function. So, and when I say it's a function, what I mean is that these two conditions that we have proven before apply. So if I have f of x equals y1, f of x equals y2, then y1 necessarily equals y2. And this thing right here, that the domain of f equals the B union C and range of f is a subclass of A, that told me that this is not just a graph, this is a function. Now, the statement here that the same exact condition apply to G composite F. So as usual, you'll have some time to think of why this can be true. Okay, so I'll proceed with the proof of this theorem. So first, we would look at, if you recall, with the graphs also. Uh, so you can already see that in set theory, so everything depends on all the things before it, since you're building a whole system. And so we will be using a lot of the things that were proven in previous classes or previous sessions. So first, the domain of G composite F is the same as the domain of F. And so that would be equivalent to A. The range of G composite F is a subclass of the range of G. And I know that the range of G is a subclass of C. Then the range of G composite F, which is a subclass of range of G, would be a subclass of C. So that's the first thing that tells me that this is a function. This is the first condition, that the domain of G composite F equals A, and that the range of G composite F is a subclass of C. So that's the first condition for it to be a function. That's the easier condition. The second condition is that G composite F of X equals Z1 and G composite F of X equals Z2. Now what I want to prove is that Z1 equals Z2. So this step would have a lot of variables, but it's just applying the definition of what a composite is. So what do I mean by G composite F of X equals Z1? Looking at the definition of the composite, this specific form of definition, f of x equals z and g of z equals y. Here what I'm saying that there exists a y1 where f of x equals y1 and g of y1 equals z1. Okay, so you can see the output of the first function, which would be y1, is the input of the second function. And the output of the second function would be this z1. So it would be g composite f of x. And the second condition then. So this is just for g composite f of x equals z1. This is the definition of it. So in this first set of parentheses, the second one is just the same. There exists some y2 where f of x equals y2 and g of y2 equals z2. Okay. Now I have that f of x equals y1 and f of x equals y2, and I know that f is a function. Okay. Now from the definition of function, since f of x equals y1 and f of x equals y2, this would mean that y1 equals y2. So that's the first step up until now. Now, since y1 equals y2, I will just remove every y2 from the whole of this definition and replace it with y1, okay? Now, applying the same logic to G after replacing every y2 with y1. So this would be there exists y1 where f of x equals y1 and g of y1 equals z1, and there exists y1 where f of x equals y1 and g of y1 equals z2. So what I will have that g of y1 equals z1 and g of y1 equals z2, since already y2 equals y1, okay? But if g of y1 equals z1 and g of y1 equals z2, and I know that g is also a function, then by definition, z1 would be equivalent to z2. So now if I have that g composite f of x equals z1 and g composite f of x equals z2, this would imply that z1 equals z2. And this is the second condition for it to be a function. And now from 1 and 2, g composite f would be a function. So even though here we introduced what seems to be many variables, we are just doing the same old thing of replacing the thing by its definition. So removing g composite f of x equals z1 and plugging in its definition, and then removing g composite f of x equals z2 and putting it in its definition. And then we just keep doing few observations, or we just observe few things like here you have f of x equals y1, f of x equals y2, f is a function, then y1 equals y, definition of f again. And then this would leave z1 and g4. And so overall, this proved that g composite f would be a function. Okay.
Actually, sorry, can you repeat the last bit? At least on my end, your connectivity was a bit wonky.
Okay, so the last part, what I was saying, that you remove the thing and put its definition in its place. So if I have g composite f of x equals z1, I just say that this is the same as putting it its definition. So I just remove g composite f(x) equals z1 and plug in its definition. And I did the same thing with the second statement. G composite f(x) equals z2. I removed it and plugged in its definition over here. And then I just noted that f of x equals y1 and f of x equals y2. What the definition of f, since f is a function, this would imply that y1 equals y2. Now, since y1 equals y2, I can remove every y2 and put y1 in place of it. And so I notice here that g of y1 equals z1 and g of y2 equals z2, but y2 and y1 are the same. So I can say that g of y1 equals z2 also. So if I have g of y1 equals z1 and g of y1 equals z2, and I know that g is a function, this would imply that z1 equals z2. And this is the second condition for g composite f to be a function. So the first condition is that the domain of g composite f equals a, and that the range of g composite f is a subclass of C. And the second is that if g composite f of x equals z1 and g composite f of x equals z2, this would imply that z1 equals z2. So you cannot have two different outputs for the same input. Okay, that's the general rule of any function. If I put the same input, I cannot get two different outputs. The opposite can happen. I can input two different inputs and get the same output. Like in the example of x squared, I can put 2 or -2, and they will give me the same output. The opposite cannot be true. So I cannot put the same input and get two different outputs for it to be a function. This is just visualization of what the composite would be. So I have, this would be f, so it's mapping from x1 to y1. G would map from y1 to z1. So the composite of the function is just mapping from a to c. So from x1 to z1 immediately. That would be g composite f. Okay. And the same thing in the case of x2, y2, and z2, etc. Okay. So this is the arithmetic example of what we're speaking of. So if I have f of x equals x squared and g of x equals x cubed, then g composite f of x would be x squared power 3. So I deal with this f of x as the input of g of x. So I remove, so this x I replace it with x squared, or I replace this x with f of x, which is actually x squared. So this would be x squared all power 3, which is just x power 6. Okay. So this would be g composite f. Okay. The last concept would be the inverse functions. So first, when I say if I have a function f mapping from a to b, when I say that f is invertible, what I mean that f inverse mapping from b to a is a function. Now, what's f inverse? That's also a concept we introduced in graphs. When we, in the same slide, we introduced the composites, we introduced something called the inverse of a graph. So we said that g -1, it should be power -1. So g power -1 equals yx, where xy belongs to g. That's in the case of a graph. Now, when dealing with functions, we use the same thing, but instead of g being an arbitrary graph, this time we're dealing with a function. So f inverse equals yx, where xy belongs to f. So f is invertible if and only if the f inverse is also a function. So if I have f is a function and f inverse is a function, only then I can say f is invertible. Okay. So this theorem would say, just a second. So first, from now on, when dealing with implication, we will make this thick arrow the implication arrow, and this thin arrow would be the mapping arrow, since it can get a little confusing when dealing with such things. So this would be the implication arrow from now on, and this would be the mapping arrow. Okay. So what this theorem says is that if f mapping from a to b is a bijection, so it's a bijective function, and bijective function is just anything that's injective and surjective at the same time. This would imply that f inverse from b to a is also a bijection. So you should have 2 minutes to think about it. The proof. First, I have the domain, since f is a bijection. So remember that a bijective function was a special case of function where not just the range is a subclass of B, but the range is actually equal to B, since projective would entail that it's also surjective at the same time. So the domain of F equals A and the range of F equals B, which would then imply, that's again from talking about graphs and such things, the domain of F inverse would be B and the range of F inverse would be A. So that's the first condition to make the function surjective. Okay, so if I have, when dealing with any function, a surjective function is a function where the range is the same as the codomain. So for this to be surjective, you have that the range is not just a subclass of B, it's equivalent to B. Okay, and for F inverse to be surjective, I would have that the range of F inverse is equal to A, not just a subclass of A. This would make it surjective. Okay, now let's first look at F inverse of y equals to x1. We're going to assume, we want to prove that F inverse is first a function, then that this function is actually projective. Okay, so that's the first condition for it to be a function, because I know that if the range of F inverse equals to A, then it's a subclass of A also at the same time. Now, to check the second condition, I would say F inverse of y equals x1 and F inverse of y equals x2. What I want to prove that x1 equals x2 in this case. Now, saying F inverse of y equals x1 and F inverse of y equals x2 is the same as saying f x1 equals y and f x2 equals y. So that's just from the definition of the inverse, right? So if I have f inverse of y equals x1, then f of x1 equals y. And if I have f inverse of y equals x2, then f x2 equals y. Now, in this case, we're dealing with a projective function, so f is a projective function. And so since it's projective, it's also injective, because that's what projective means, that it's injective and surjective. So we said that for injective functions, if f of x1 equals y and f of x2 equals y, then x1 equals x2. That's the thing that we said in the last session. From the definition, that's what it means to have an injective function. That if I put two inputs and they yield the same output, then these two inputs must be equal. Okay. And so that's why we said the last time that x squared is not an injective function, since you can put 2 and -2 and get the same output. Then it was not injective unless you change the domain, of course, to R positive or to Z. So the fact that fx1 equals y and fx2 equals y, and the fact that f is actually an injective function, this would imply that x1 equals x2. So now looking at these two statements, 1 and 2, I can say that f inverse is actually a function. Okay, since the range of f inverse is a subclass of A, since it's actually equivalent to A, and since f inverse of y equals x1 and f inverse of y equals x2 imply that x1 equals x2. That makes f inverse a function. So it satisfies the two conditions for it to be a function. Now, we want to prove that this function is actually a projective function also. So first, for surjectivity, it's already proven above that the range of f inverse equals A. So that makes it surjective, not just a subclass of A, it's actually equivalent to A. Now for the injectivity, so I'm going to say f inverse of y1 equals x, f inverse of y2 equals x. I want to prove then that y1 equals y2. You should not say that the difference between it being actually a function in the first place and it being injective. If you look here at first, we have the same input and two different outputs, and I want to prove that these two outputs are the same. That's for it to be a function. For it to be injective, I'm having different inputs and the same output, and I want to prove that these inputs are equivalent actually, or the same inputs. Okay. And so if I have f inverse of y1 equals x, this is the same as saying f of x equals y1. So this is again applying the definition of the inverse. If I have f inverse of y2 equals x, then f of x equals y2. Now I know that f is actually a function. Since f is a function, then y1 has to be equal to y2. And this makes the f inverse actually injective. And so since f inverse is both injective and surjective at the same time, then f inverse is a projective function. So you can also, when we say that to prove that f inverse is a projective function, you have to prove the two statements. First, that it's a function in the first place, using the above conditions, then that it's actually projective. Okay. So that's an example of the inverse function. So if you look at these two classes, so if I have f of x1 maps to y1, then f inverse of y1 maps to x1. If I have f of x2 maps to y2, or equivalent to y2, then I have that f inverse of y2 gets me back to x2, okay? So you can notice that these are just the exact opposite functions. So this maps from a to b, this takes the same element but maps it back to a, okay? I think that's the last theorem would be that f inverse, if I have that f inverse maps from b to a is actually a function, then f mapping from a to b has to be a projective function. Again, just 2 minutes to think about why it's true. Dealing with the proof. So first, the domain of f inverse equals b. So that's just because I'm saying that f inverse is a function. Okay, this would imply that the range of f equals b. So that's again from the definition of what an inverse is. That the domain of the inverse is the range of the original function, and the opposite is true. So if I have the domain of f inverse equals b, then the range of f equals b. And that's first the case of it being surjective. So since I have the range equals this codomain, then the function, then f is surjective. So that's the first condition. The second condition, I have f of x1 equals y and f of x2 equals y. I want to prove that x1 equals x2. That's for it to be injective. So first, this would imply that f inverse of y equals x1 and f inverse of y equals x2. So that's again applying the definition of what an inverse is. Since f of x1 equals y, then f inverse of y equals x1. And since f of x2 equals y, then f inverse of y equals x2. Now, I'm given that f inverse is a function. Since f inverse is a function, you cannot have the same input with two different outputs. Therefore, x1 has to be equivalent to x2. But since f x1 equals y and f x2 equals y, and would imply that x1 equals x2, then this function is injective. Since the function is both surjective and injective, then f has to be a bijection. And these two last theorems can be just concluded in the idea that f from a to b is invertible if and only if f is a bijection. So if you have any function that's not bijective, then it cannot be invertible. Then this function cannot be, you cannot find the inverse of this function unless the function is bijective, okay? So I think that's the last theorem. I think that wraps the session for today. If you have any questions, you should leave them in the chat or just unmute yourself and say them.
Will you be able to make it to tomorrow? All right. Thanks for coming. Bye.